Welcome to today's lesson on neural networks. In this video, we will explore the fascinating world of neural networks and how they mimic the behavior of neurons in our brains. Let's dive in. Can you imagine a world where machines can think and learn just like our amazing brains do? Yes, it's becoming true with the advent of artificial neural networks, which is actually a subset of machine learning and in turn a subset of artificial intelligence. Artificial intelligence applies to computing systems designed to perform tasks usually reserved for human intelligence. Machine learning is a subset of artificial intelligence that utilizes advanced statistical techniques to enable computing systems to improve at the task with experience over time. Actually, the story is once upon a time, in the land of computer science, researchers were inspired by the remarkable capabilities of the human brain. They marveled at how our brains process information, makes decisions, and learn from experience. And thus the concept of neural network was born. So today we are going to board on a journey into this captivating empire of neural networks, where we will discover how these incredible systems mimic the behavior of our very own neurons. So fasten your seatbelts and get ready for an adventure. Before we dive into the magical world of neural networks, let's take a moment to appreciate the wonder of our own brain and its extraordinary neurons. Just imagine a peculiar world inside our brains where there are tiny cells called neurons which work together to create amazing achievements through intelligence. Just imagine billions of tiny cells called neurons bustling with activity, forming an intricate web of communication. These neurons receive information, process the information, and transmit the information through electrical and chemical signals, thus creating the complex tapestry of our thoughts, memories, and actions. Now let's embark on our adventure into the world of neural networks, where we strive to replicate the amazing abilities of our brain's neuron. In the world of brains, there lived a bunch of special cells called neurons. These neurons were like the rock stars of the brain. They had the power to transmit information using energetic electrical signals. They were the ultimate superheroes of the brain's secret home. Creating a copy of natural brain is just the artificial neural network. Let's take a close look at how these mighty neurons behave as it boils down to three essential processes like reception, integration, and transmission. Think of neuron behavior as the three soldiers, each with its unique role. Let us go to the 3 soldier operation. 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 The 3 soldier operation The first soldier or our first hero is the reception. Imagine this as a friendly little soldier with outstretched arms, eagerly waiting to receive messages from other neurons or from the outside world. They are like tiny receivers catching information just like baseball players catching a ball. The next soldier we have is integration, the brain's master chef of information. Imagine this soldier as a peculiar chef in the kitchen, taking the received messages and mixing them together in their special natural blender. These soldiers actually stir, they mix, they process, and we have the magnification blend of insights and ideas. But what's missing now is the crucial part, the transmission. Think of it as a soldier in superhero capes, ready to take their newly created mix of information and send it off to other neurons. They shoot electric signals like lightning bolts, which are zooming through the brain's superhighways, passing on knowledge and power of their mix to all other neurons in the network, while transmitting to other neurons through junction points called synaptic gap. The strength of the message can be modified through a process known as synaptic plasticity. So in the kingdom of neural network, we have interconnected units known as neurons or nodes. Just like the neurons in our brain, these artificial neurons will also receive input signals from other neurons, process them using mathematical functions, and produce an output signal which is shared to all other neurons. It's as if we are creating an virtual brain. So in order to understand the neural network, let's unravel the concept further. These neurons are like a bunch of chatty friends. Just imagine. The neurons are like bunch of chatty friends, each with its own personality. These friends love to communicate with each other through special connections called synapses. It's like they are passing notes in class, but in a super cool, electrifying way. Now let's spy on the conversation between these neurons. Just picture them as sitting around in a crazy coffee shop, sipping digital cappuccino and discussing the meaning of life. It's the drama. So when one neuron has something important to say, it shouts out its output, which serves as the input to the next neuron in the network. So I can say it's like a relay race, where each neurons pass the baton of information to its teammate. But here is the twist. Each neuron is a bit of multitasker. It receives input from multiple neurons, put on its thinking cap, and comes up with its own brilliant output. It's like a neuron party where everyone has unique dance move to show off. Just wait. There is much more. The brainy superpowers of neural network don't stop there. This network has the ability to learn and adapt, just like how we humans grow wiser over time. The interconnections between the neurons are like elastic bands that stretch and flex. They enable neural network to learn from data, discover patterns, and even improve their accuracy. It's like this network are doing a grand glow up, becoming smarter and smarter with each and every new experience. Now, let's zoom in to a single neuron and explore its key components, just like we are investigating a detective toolkit. First, look at the figure. We have the cell body, also known as soma. It is like the brain's headquarters, housing the nucleus and other essential cellular structures. Think of it as control center where all the important decisions are made. Next, imagine the neurons dendrites as roots of tree reaching out to catch signals. They are like tiny arms eagerly waiting for information from other neurons or sensory organs. They are the receptors, always ready to receive informations. Now let's move on to axon, a long cable-like projection that carries electrical signals away from the cell body. It's like a superhighway conducting the neurons' messages and speeding them to their destiny. Finally, we have the synaptic gap, which is like neuron's secret engagement point. These small branches at the end of the axon are called synapses. It's where the magic communication happens. Just imagine our neurons as lively characters attending a fancy party. They wear their finest outfits and bring along their trusty bags called synapses, filled with chemical messages called neurotransmitters. When the neurons want to send a message to another neuron, it releases these neurotransmitters at the synaptic gap. It's like passing little notes between friends, filled with secret codes and information. The receiving neuron catches these messages from the synaptic gap using their dendrites. Now then, we have explored the incredible components of natural neuron. Let's now shift our focus to their artificial counterparts in neural network. These artificial neurons or nodes have a similar structure and play a vital role in simulating the brain's intelligence. In a neural network, a single artificial neuron has several components. First, it receives input from other neurons or external sources, just like our natural neurons receive signals. But there is a twist here. Each input has a weight assigned to it. The weights determine the importance or significance of each input. Just like some messages carry more weights than others. It's like giving priority to certain clues in a detective investigation. The inputs got multiplied by its corresponding weights to produce weighted sum of inputs. The next is bias. To spice things up, our artificial neuron also has a bias. It is just like a sort of preference or inclination. It's like a neuron saying, hey, I may need a little push before I decide to speak up. Shall we uncover the hidden role of our mischievous friend bias? Yes. It's like an additional constant term that tags along with the weighted sum of input. Think of it as neurons' adjustable mode or activation threshold. Actually, the presence of bias allows the neuron to have its own preference, its own eccentricity. It influences whether the neuron should activate or remain inactive for the amount of inputs which it receives. But here is where things get really exciting. Bias introduces a level of non-linearity to our neurons' response. This makes our neurons a playful creature that doesn't allow that doesn't like to follow a straight or predictable path. Without this bias term, the neuron's response would be solely determined by the weighted sum of inputs, which is a linear function. It is like a robot sticking to strict rules. But with the addition of this bias, our neurons' response becomes more flexible and dynamic. By adjusting the bias, our neurons can shift its activation threshold, capturing the twist and eccentricities of the data. It becomes capable of representing more complex relationship and capturing nonlinear patterns. It's like our neurons saying, I am not just an robot. I can understand the nuances and mysteries of the world. And now we are about to unlock the secret of activation function, a mathematical twist that determines the fate of our neurons, that determines the output of our neurons. Get ready to explore the fascinating world of these functions and discover how they shape the behavior of neural network. Just imagine our neurons as peculiar performers in a grand stage. They possess an extraordinary ability, the power to activate or remain dormant based on a mathematical magic trick. Now let's dive into the heart of neuron, which is nothing but the activation function. It's like the ultimate decision maker, determining whether the neuron should fire up or stay silent based on the computed value from its inputs, weights, and bias. So imagine our activation function as magical sticks waving in the air to cast their spells on our neurons. Each function has its unique charm, transforming the neuron's output in a specific way. And now let's see some popular activation functions. First we have is the step function, a binary magician, I can say. It sets a threshold, and if the computed value, the sum of weighted inputs plus the bias exceeds the threshold, it outputs 1. And it's activating the neuron. If it is below the threshold value, its output is 0, equivalent to silent state. So with this activation function, our neuron is acting like an on-off switch. Next we encounter the sigmoid function, which is a smooth operator. It produces a beautiful S-shaped curve, mapping inputs to a range between 0 and 1. It's like a neuron with a flexible attitude, gently transiting from inactive to fully active as the computed value changes. And next activation function is ReLU, rectified linear unit. It is a board performer. This function sets negative input to 0, and it embraces only positive values. It's like a neuron with a strong preference for positivity and saying no to negativity and yes to positive vibes. And next is the hyperbolic tangent function. It is a smooth cousin of sigmoid. It also maps input to a range, but this time between -1 to 1. Sigmoid ranges from 0 to 1, but hyperbolic tangent ranges from -1 and 1. It's like a neuron with a broader emotional range, expressing both positive and negative sentiments. And last but not the least, we have a glamorous soft max function. I can say a star in multi-class classification task. It produces a probability distribution over multiple classes, allowing our neurons to choose the most likely class. It is like a neuron with a gift or diplomacy, assigning probabilities and making fair decisions. And these activation functions are true magicians of neural network. They add depth, complexity, and adaptability to our neurons' behavior. And by applying these mathematical spells, we transform the raw computations into meaningful outputs, enabling our neural network to make predictions, classifications, and much more. Coming to the working of single neuron, let's consider an example. A neural network or a neuron which is having n number of inputs, say from x1 to xn, x1, x2, x3, etc. up to xn. This input can represent anything from pixel intensities in an image to numerical values in a data set. So alongside with this input, our neuron possesses n corresponding weights ranging from w1 to wn, w1, w2, etc. up to wn. Think of these weights as the neuron's preference or priorities assigned to each input. But wait, there is one more thing. Our neuron also carries a special item called bias, a constant term denoted as B. This bias adds a touch to our neuron, influencing its activation threshold and decision-making process. It's like the neuron saying, hey, before I make up my mind, let me consider my preference and additional factor. Now our neuron is ready for action. It's time for magical transformation to begin. The inputs x1, x2, x3, etc. and their corresponding weights w1, w2, w3, etc. comes together in a beautiful dance of multiplication. Our neurons takes each input and multiplies with its respective weight. These individual products represents the neuron's preferences and how strongly it values its input. It's like our neuron assigning importance to different aspects of the information it receives. Once the inputs and weights have been multiplied, our neuron performs a grand act of summation. It adds up all these weighted products, creating a single value, a sum of their combined influences. It is like our neuron gathering all these signals and whispers from the inputs, merging them into a constant message. But our neuron's journey doesn't end here. There is still one more step to complete its magical transformation. In the final step, our neurons encounters the wondrous sigmoid activation function or some other activation function which we have discussed. It gives a magical touch that shapes its output. So the sum of weighted inputs along with bias now enters the sigmoid function, and something extraordinary actually happens here. The sigmoid function performs its mathematical witchcraft, transforming the summed value into a smooth S-shaped curve. The curve represents neuron's activation level, the intensity of its response. So it is like the neurons taking a deep breath and deciding, based on this input and my preferences, I will decide how much I have to speak or I have to stay silent. So the transformed value emerging from the sigmoid function becomes the output of the neuron, the result of its computation, and that is the decision making process. And so, dear adventurers, we have reached the end of our extraordinary voyage into the kingdom of neural networks, and we have introduced the mysteries behind the behavior of neurons and how they inspire the design of artificial neural network. Through interconnected units, the neural networks channel the spirit of neurons, processing information, making decisions, and modeling complex relationships. Here, inputs, weights, bias, and activation functions work in harmony, giving birth to computational wonders that powers our modern technological advancements. Just as our brains weaves together countless neurons to create magnificent tapestry of human intelligence, neural networks comprise of neurons organized as input layer, hidden layer, and output layer, or to harness the collective power of interconnected units and tackle innumerable tasks, which ranges from image recognition to natural language processing and even autonomous driving. So, the artificial neurons make connections with each other and arrived as input layer, hidden layer, and output layer is just shown in this figure. And as we move on, let's remember the remarkable parallel between the integrate working of these neurons and the computational marvel of this neural network. Actually, the story of neurons and neural network continues to unfold, inspiring innovation and shaping the future of technology. So, my fellow adventurers, embrace the wonder and potential of neural network. Let your curiosity guide you as you dive deeper into this captivating field. The possibilities are endless, and the magic of neural network awaits your discovery. So, thank you once again for joining me on this enlightening journey. Until meet again, keep exploring, keep questioning, and keep unlocking the secrets of this universe. Neurons fire, network grow, a word of knowledge begins to flow. So let's journey forth, mindsets free, embracing the wonders of this neural network as we unlock our destiny. So, thank you one and all. Thanks a lot.